Auroras are created when charged particles emitted from the sun during a solar flare penetrates the Earth's magnetic shield and collide with atoms and molecules in our atmosphere. These collisions result in countless little bursts of light called photons, which make up the aurora. Auroras can be seen above the magnetic poles of the northern and southern hemispheres, Aurora borealis in the north and Aurora australis in the south. It is difficult to predict when you can see an aurora, but usually winter is a good time due to the darker nights.
The negative effects of Aurorae on civilization. 1. Radio communication. Because the Aurorae disturb the atmosphere, radio waves can be disturbed that communicate information from around the world. Another way is electricity. Solar wind adds magnetic energy to the Earth's own wind, causing them to blow out electric cables and wires that they blow past. Falling satellites is also another issue that comes from Aurorae. When Aurorae interact with the Earth's atmosphere, the atmosphere slightly expands, bringing any low-flying satellites into the upper atmosphere. This can slow them down enough to eventually lose momentum and fall back to Earth.
In past history, many cultures created mythological legends surrounding auroras. The Romans, for example, associated the aurora borealis with their goddess of dawn, Aurora, which is a Greek word for sunrise. In the early modern period of Europe, a rare sighting of the aurora was considered to be a bad omen, which is most likely due to the fact that intense solar activity led to the lights being completely red. In China, the aurora was seen as a battle between good and evil dragons, and the redness was caused by the evil dragons breathing fire. In Australia, where the Aurora australis occurs, the aurora was sometimes seen as a message from the spirit world, or an omen associated with fire. Auroras are known for their emission of vivid colors. These colors that an aurora produces is determined by the atmospheric gas that is present in the atmosphere, and by how excited these gas particles are, meaning the energy of the charged particles from solar wind that collided with it. The resulting colors emitted after the collisions can be determined on a wavelength scale. For example, the color red is associated with the presence of excited atomic oxygen and intense solar activity at high altitudes, and has a wavelength of 630 nanometers at the most. The green color is most common and is associated with less excited atomic oxygen at lower altitudes, and has a wavelength of 557.7 nanometers. Blue and purple colors are associated with even lower altitudes and the presence of ionized nitrogen, and has a wavelength of 428 nanometers. The blending of these colors can result in yellow, pink, or purple hues.
Auroras on other planets. Auroras are not exclusive to Earth. The gas planets, Jupiter, Saturn, Uranus, and Neptune, all have their auroras because of their heavy atmosphere and strong magnetic field. Scientists know this because of machines that take measurements, such as the spacecraft called Cassini and images from the Hubble Space Telescope. The colors of their auroras are different from our planet because of the gases in their atmospheres. Their magnetospheres are different as well. However, the same ideas apply to their auroras and are not much different from Earth. Around Jupiter, the blue aurora is affected by the moons created by the solar wind. The moon, low, spews out many charged particles in the magnetosphere, which causes huge electrical currents and beautiful blue, ultraviolet aurora.
Auroras is the product of magnetic fields of the Earth and Sun and of the solar wind. The origin of Earth's magnetic field is not completely understood, but is thought to be associated with electrical currents produced by the coupling of convective effects and rotation in the spinning liquid metallic outer core of iron and nickel, also known as the dynamo effect. When charged particles from the sun strike air molecules in Earth's magnetic field, they cause those molecular atoms to become excited. The molecules give off light as they calm down. A fundamental property of magnetic fields is that they exert forces on moving electrical charges. Thus, a magnetic field can trap charged particles such as electrons and protons as they are forced to execute a spiraling motion back and forward along the field lines. Great storms on the sun send gusts of charged solar particles hustling across space. If Earth is in the path of particle stream, our planet's magnetic field and atoms react. When charged particles from the sun strike air molecules in Earth's magnetic field, they cause those molecular atoms to become excited. The molecules give off light as they calm down. A fundamental property of magnetic fields is that they exert forces on moving electrical charges. Thus, a magnetic field can trap charged particles such as electrons and protons as they are forced to execute a spiraling motion back and forward along the field lines. Great storms on the sun send gusts of charged solar particles hustling across space. If Earth is in the path of particle stream, our planet's magnetic field and atoms react.